Hi all, I'm Sowjanya Karri, currently working as Principal Technical Engineer in Oracle. And today I want to talk about this topic, explainable generative AI models for anomaly detection in transactional finance data. So, anomaly detection in financial transactions is the critical component in combating fraud, ensuring regulatory compliance, and safeguarding user trust. With the exponential growth of digital transactions in the financial sector, the threat has significantly expanded and making anomaly detection a very critical component. Anomaly transactions, often indicative of fraud, money laundering, require timely and accurate detection mechanisms that can adapt to evolving patterns and behaviors. Traditional rule-based systems, and even some machine learning models, fall short in detecting these anomalies in high-dimensional and dynamic financial data. In recent years, deep generative models such as variational autoencoders and generative adversarial networks have shown very promising in modeling the normal distribution of transactional data and also identifying outliers based on reconstruction error or latent space deviation. However, despite their accuracy, the lack of transparency and interpretability in these models in regulated financial environments where decisions must be auditable and explainable. So, this research aims to bridge the gap by integrating explainable artificial intelligence, which is known as XAI, methodologies into generative AI models, enabling not only robust anomaly detection but also transparency and trust in financial decision systems. So, while the quick digitization of financial services have greatly increased convenience, it has also led to an increase in unusual and fraudulent activity. Finding anomalies that can point to fraud, money laundering, or data tampering has become crucial given the millions of transactions that take place in real time. Generative AI models such as variational autoencoders and GANs. So these autoencoders have gained popularity for their ability to learn complex distributions and also identify irregular transactions without needing explicit anomaly labels. In order to get around this, more and more academics are looking into combining generative models with explainable AI. Deep learning is being used in conjunction with methods such as SHAP, attention mechanisms, and interpretable latent spaces to improve transparency without sacrificing any performance. So, this combination creates new opportunities for creating reliable, interpretable, and also to accurate fraud detection systems. While deep generative models like VAEs have demonstrated strong performance in detecting anomalies in financial transactions, their inherent black box nature presents a serious challenge in real world deployment. Financial institutions operate in heavily regulated environments where automated decisions must be transparent and auditable. Current generative models often lack mechanisms for explaining why a particular transaction was flagged as anomalous and limiting user trust and regulatory acceptance. Moreover, although post hoc explanation tools like SHAP and LIME are commonly used, their predictions, they are rarely integrated with the model's architecture, which is leading to inconsistencies between predictions and explanations. There is a critical need for a unified approach that combines the anomaly detection capabilities with built-in interpretability features and enabling both high detection accuracy and transparent decision making. And the primary objective of this research is to develop an explainable generative AI framework for detecting anomalies in financial transaction data. Specifically, the model aims to integrate variational autoencoders with attention mechanisms and SHAP-based explanation layers to achieve both high anomaly detection accuracy and interpretability. So here in this research, we proposed an explainable VAE framework that that integrates attention mechanisms with the decoder and incorporate SHAP values to enhance interpretability of anomaly detections. And we conducted extensive evaluations on the IEEE-CIS fraud detection dataset, which has very competitive performance compared to the baseline models such as isolation forest, standard VAE, etc. And for financial decision systems to be transparent and trustworthy, explainable AI is very essential. In order to help analysts comprehend model predictions, methods such as SHAP offer feature attribution based on the Shapley values. So this is the proposed framework where the data set is mainly divided into two primary data, like the train transaction CSV, which contains transactional features such as transaction amount, product type, card details, and email. And the other one includes transactional features such as device type, browser, screen resolution, and operating system. So model performance and generalizability depend on high quality data pre-processing, particularly in delicate areas like fraud detection. Despite having many features, the dataset has a large number of missing values, anonymized fields, and inconsistent entries that may interfere with learning. To deal with this missing data, we need to align identity and transaction files without affecting the essential transactional patterns. So this proposed framework integrates the variational autoencoders with the attention mechanism and SHAP-based explanation to enable both anomaly detection and interpretability. And as shown in this picture, pre-processed transaction data is passed through the encoder to generate a latent representation, which is then refined using an attention layer to highlight important patterns. And this enriched latent code is used by the decoder to reconstruct the original input, and the anomalies are identified based on the reconstruction address. In parallel, the latent representation is also processed by the SHAP-based explanation, which generate feature attributions offering insights into why a particular transaction was flagged and anomalous. The model also incorporates an interpretability aware loss to encourage transparency in learning. This architecture ensures a balance between accuracy and explainability, which is very critical in financial systems. In addition to acting as the information bottleneck, the latent space is very essential for identifying underlying transaction patterns. Using the latent representation, the decoder network recreates the initial input. The decoder incorporates an attention mechanism to enhance interpretability and focus. And this technique effectively highlights which features contribute more to each reconstruction by learning to give dynamic weights to various latent dimensions. So these are the results. So the experimental design, baseline comparisons, and performance assessment of the suggested explainable framework are presented in this section. So to validate the performance of proposed explainable VAE framework, we compared it against three widely used baseline in unsupervised anomaly detection. So isolation forest, we already know, a tree-based assemble model that isolates anomalies through recursive partitioning. Standard VAE, which is without any attention or SHAP, which is used to test the impact of interpretability layers. GAN anomaly is a GAN-based anomaly detection method using encoder, decoder, encoder structure. So these baselines were selected due to their popularity and success in fraud detection settings. And the performance of all these models are assessed using standard classification metrics derived from the confusion matrix, the precision, recall, F1 score, and AUC. Precision is the proportion of predicted frauds that were actual frauds. Recall means the proportion of actual frauds that were successfully detected. F1 score is the harmonic mean of precision and recall. AUC is the area under ROC curve, which measures overall discriminative ability. So So this is a other results slide where we can see the proposed model outperformed all baselines across precision, recall, F1 score, and AUC metrics. The proposed model achieved strong performance across multiple metrics, outperforming baseline models on both detection and interpretability. So as shown here, the precision is 0.81, recall is 0.72, F1 score is 0.76, and AUC score is 0.91. So this demonstrates the model's ability to effectively detect fraudulent transactions while maintaining a low false positive rate. So the suggested explainable VAE effectively strikes a balance between interpretability and detection performance. And also we have a few limitations exist. The SHAP computation is resource intensive, and model performance may downgrade in real-time streaming due to retraining needs. But still, the framework lays a strong foundation for future enhancements such as hybrid models with transformers or multimodal learning involving transaction text and metadata. So, in order to detect anomalies in financial transactions, this study suggested an explainable generative AI framework based on variational autoencoder coupled with attention mechanisms and sharp explanations. The model met the requirements for accuracy and interpretability in regulated environments by successfully identifying fraudulent values. With an F1 score of 0.76 and the AUC of 0.91, the experimental findings on the fraud detection data showed very good performance. Though integrated explanation layers, the suggested approach demonstrated enhanced anomaly identification while preserving interpretability when compared to baseline models. This approach can be improved for computing efficiency and expanded for real-time fraud detection in subsequent work. Further improving performance and scalability in financial systems may involve investigating transformer-based or hybrid designs and integrating multimodal data sources. Thank you.
Thank you so much for that presentation. It was very in depth on the research, and I really liked how it put together the different processes and methodology while explaining all the different technical elements. So we do have a few questions. First from Ethan Hatif. What does a day in the life look like for you as a technical engineer at Oracle?
Yeah, it's good. Like we are learning, a lot of things every day from work, and also internally we have we have Oracle learning and all, where we have lot of topics and sessions available. So we used to attend those sessions, and we improve our growth by going through different certification courses and then writing those certifications, and improving skills in the day-to-day activities.
Yeah, so we have another question from Stephen Navarro right now. It's saying, what inspired you to get into tech and work with tech engineering?
Yeah, so I felt like the tech engineering is challenging because we have a lot of things to improve, learn, and also we have more leadership roles. So if we have any goal to have a leadership in any future projects, or if we have a dream of doing any leadership activities in future, I felt like the tech industry is very good platform to work on it. Yeah.
Yeah.
And then another question from Ethan Hatif. In terms of computational efficiency, I think you mentioned that around there and also at the end. What are metrics and ways to improve it?
So I felt like in so many, we are still lagging on identifying some suspicious behavioral activities where we need to improve that. And to do that, we need to make our model and train the model with more testing data with different types of anomaly detection data sets and all, so that we can have good improvement in those areas.
Yeah, so before we leave off, I'd just like to say that was an incredible talk. I think we really dove into the technical elements of like the architecture. I think that really resonates with us here as well because of the amount of technical work we do to keep our platform up and
There is always an opportunity to contribute to the discussions that we have at EnviroCast Geo. If you are interested in attending or even speaking at a future conference, learn more at geo.envirocast.org. We're excited to hear your insights.